next presentation, which will be by two of our young trainees on high product electromagnetics, so Mohammed AlKaabi and Mohamed AlYousef. Just to give a couple of words about them. So they belong to the electromagnetics group. They are currently with DERC. They've been for a year with DERC. So Mohammed AlYousef, he's a mechanical engineering from Khalifa University. He did his master's in energy systems in Queen Mary University in London, and has been with us, as I mentioned before, for the last year and a half. And Mohammed AlKaabi, it's an electrical engineer from the UAE University, and they will be talking about something that Milos already explained before, slightly, but they're going. I wanted them to talk about their experience as makers, and let's say working at the same time in very short timelines, which I believe is the key point of this presentation, so that you can highlight the importance of rapid prototyping. So Mohammed, both Mohammeds, I'll give you the floor, and thank you for your presentation.
Thank you very much, Nicholas. So good morning, everyone. So I hope that you find that our presentation is quite interesting to you, and that it is informative, and that you walk away with some of our shared experience that we had at Makerspace. So in our presentation, we'll be discussing tackling emerging problems with fast prototyping. And this is mainly connected to COVID-19 in this case. So my colleague Mohammed AlKaabi and myself, Mohammed AlYousef, we'll be sharing our experience at Makerspace Al Zeina as part of the Citizen Science Initiative during combating the COVID-19 pandemic. And we hope that we can have a very fruitful discussion, or perhaps some questions that we can address in the Q&A session after the presentation. First of all, we would like to extend our deep gratitude and thanks to Makerspace Al Zeina, who provided us with the necessary tools, equipments, expertise even, without whom this project wouldn't have been as successful or even possible. So thank you so much for that. We would also like to take the opportunity to thank the Advanced Materials and Research Center in joining forces with us while combating this pandemic. As we have Dr. Mohammed AlTaneji, the Chief Researcher of the AMRC, and the engineer and designer JD, who was also a critical part in the design process. Of course, not to forget to mention our center, the Directed Energy Research Center, Dr. Shawqi Qasmi, the Chief Researcher, Dr. Felix Vega, the Electromagnetic Radiators Director, Dr. Nicholas Mora, the moderator today and the Electromagnetic Effects Director, Milos Miryak, the Director of Signals and Electronics, who just previously gave us a talk, a very interesting talk. Also, one of the very important, let's say, team players and critical members and part of this project that we have to mention are the following: Abdullah Al-Ali, Ali Al-Ali, Hamad Al-Yahyai, Hassan Al-Hammadi, Hind Al-Kitbi, Juan Galvez, Mariam Al-Minhali, myself, Mohammed AlKaabi, and Shahab Al-Dahmani. So thank you, everybody, and you are all part of this project, and credits to everyone mentioned and others who are also part of this project. So just to give you an idea about the agenda of this presentation. Now, I know it's already been around 2 hours and most of us are fasting, so we'll try not to take too much of your time. We'll keep this as efficient as possible. Should take about 20 minutes, so please bear with us. The agenda will go as follows. We'll start with the motivation. We'll give you a little bit about the brainstorming aspect, and then we'll go a little bit into the research, and then we'll go into something we refer to as dose calculation. You'll understand more what exactly it means. Then we'll move to the prototyping. We're all familiar with that. And then finally integrating a final build. And then we'll share some of our final thoughts. So basically we'll walk you through the process in which the rapid prototyping, let's say, approach was used to combat this unprecedented pandemic. So for the motivation aspect of this project, I think it's quite, it's quite self-explanatory. We all faced a global unprecedented pandemic and COVID-19. So the world has faced several problems that really cannot really be listed. They're endless, and some of which are definitely life-threatening. And those require very, very rapid, quick, and creative solutions. So as of any project, one of the first parts or steps before designing is brainstorming. And my colleague Mohammed AlKaabi will talk a little bit about that part, and hopefully you'll find it informative.
Thank you, Mohammed, for the introduction. And now, since we have, our motivation, which is solving the problem and trying to help with solving, finding solutions for some of the problems that we faced during this pandemic. So we started by brainstorming. So our goal was to extend the personal protective equipment, which was a problem in the beginning, as we remember. And so we found two ways of doing that, or mainly it's making new resources or reusing existing ones. So making new resources can be achieved by multiple ways, some of which are creating new manufacturing techniques, or maybe 3D printing, and also manual crafts like sewing and other. And for reusing existing resources, we thought that disinfection of the virus would be the way to go on that. So having this very quick brainstorming and the idea and the goal and the motivation behind these prototypes. So the next step would be to do some research and look into how can we solve this problem. So first we saw what happened in the past, for example, for the SARS virus, which is very closely related to the newly virus COVID-19. So we found that there are multiple ways to disinfect viruses, for example, using ozone, using UV light or some chemicals. So we thought that we'll go with the ozone or UV light and see how can we solve that. So each have some positives and negatives. For example, the ozone is less effective against porous material, but it's good for complex systems that have places that the light cannot reach. Whereas the UV light, the good thing that it's very good with clothes and textiles, and also for like example phone screens, for example, that can be used by multiple people, or tablets and so on. So to compare to further research into this, we looked into, for example, for the ozone, how long does bacteria or viruses or fungi has to be exposed for, and what's the concentration of ozone for us to be able to disinfect. And we did, as you can see in the left, some small experiment on yeast, which is a type of fungi, to see what's the exposure time required and what's the concentration of ozone. Further, for the research for the ultraviolet light, we looked into different UV lights, like for example UVA and C, and we saw from literature and from some papers that UVC is very effective against SARS virus, but at the same time it has, as it is in the almost 250 to 260, almost 255 nanometer wavelength, it has some side effects also on the skin. So for that, we will have to take some considerations in our design. So so now since we have done some research into the ultraviolet light and how to disinfect with, and the ozone, for further research we will have to do some dose calculation, as mentioned in the beginning. So how long do we have to disinfect the items for? And for this, I will leave it with my colleague Mohammed AlYousef.
Mohammed, for the insight on the research aspect. And hopefully I'll walk you through some of the basics about the calculations, those calculations that we went through. So regarding the ultraviolet disinfection or the UVC disinfection calculation. So one of the most important equations is to calculate the energy, the radiated energy from the light bulb, which is by the very well known having the Planck constant multiplied by the frequency, or in this case, the Planck constant times the speed of light divided by the wavelength. Moreover, the dose, which is joule per meter squared per second, can be calculated by having power divided by, the kind of the radial area of, of which the bulb is emitting. So finally, to calculate the time of this ultraviolet disinfection, we needed to reach 67 joule, and that is from literature. This is the dose required. So if we divide the 67 by the dose per second and multiply it by the area of the target, it's going to give us our time to reach the desired dose. It will give us in seconds. So to give you a little bit about the ozone disinfection calculation, which is a totally different project in which we used ozone to disinfect, and we'll walk you through more details about this project. We used a certain room size. In this case, it was 100 meter cube. We had a certain ozone input, 5 grams per hour, and the target ozone concentration in ppm was 2.5. Now, the equation is as viewed in the slide here. The target ozone in grams can be calculated by multiplying the density of ozone, which is 2.14 milligrams per meter cube, by the ozone concentration in ppm, which in this case is 2.5, multiplied by the room size, and then divide all that by 1,000. Now, to get the disinfection time in minutes, which is the most reasonable unit in this case, or the scale, is we just divide the target ozone in gram by the input of the ozone in gram per hour, multiplied by 60 minutes. Now, that's only the time needed to reach the desired ozone concentration. However, we have to also add the time needed to actually disinfect, because we've reached that concentration of ozone. However, to fully disinfect the virus, we need a certain time. And according to literature, it was roughly about 30 minutes. So that's what we accounted for in our initial calculations. So now to walk you through to the, one of the interesting parts, especially for us engineers, it is the designing and prototyping of the project. So I'll first walk you through one of our projects, or which is the 3D masks, or the 3D printed masks. As you can see, we have some images here labeled from 1 to 4. One is basically one of the 3D printers, and 2 is just a rough sketch of how we think the mask would look like. As you can see, the yellow part would be the removable filter, which is shown in number 3. We'll talk you more about what material was used in the final build. It will be covered later by my colleague. And number 4 is the 3D printer in action. So when we actually printing the masks, and those masks were actually designed on 3D modeling software. And they were, something unique about them is that they were actually customizable, in which they would fit different sizes, facial features. And so lots of facial recognition, AI was put into this, and credit goes to our colleague Juan Galvez, which was a critical part of this project here in identifying those facial features. Now, to walk you through a little bit about the design process of the ozone disinfection chamber. Now, we have a bunch of interesting pictures here labeled from 1 to 6. So starting off with 1 is just the initial sketch, or the initial, let's say, model that we had, in which is just the whole thing is the chamber, and we have some sort of generator into the system. And so the next step for us was to actually understand what is an ozone generator. So what we did is we just got an ozone generator off the shelf, and as what engineers like to do, we started, playing with it. We disassembled it. We started to understand what's happening here. Component by component, and with some coding and some, circuiting with Arduino, we were able to understand how it operates, and we were also able to manipulate it so that we can control the time delay. We can control the input of the ozone sensor, which we integrated into our circuit. Later on, we had some sort of 3D model, which was finalized, as you can see in number 6, which we kind of reached or achieved after some testing, and after getting our own build of an ozone generator rather than using off-the-shelf one. So we'll walk you through now the third project, which is the ultraviolet disinfection, or the UVC disinfection. Walking through the design process, it really starts as shown in number 1. It starts with a sketch. This is the idea. We want a disinfection chamber that uses UVC and some sort of relay module, as a loop of whenever you have some sort of, let's say, equipment that you want to disinfect, you know exactly how much time it requires and so. And again, it starts with a 3D model, initial 3D model, where you have just a chamber and you have the UVC in there. And you go around the market and see what exactly the proper type of UVC bulb is used. So all of that, again, was based on the research that was mentioned earlier by my colleague Mohammed AlKaabi. So there is a lot of research that has been put into this just to understand what exactly is the science behind disinfection. Then later on is actually 3D modeling the final build. And that was done through, as you can see, number 5, it's a 2D drawing. So that's actually a drawing that was, let's say, uploaded onto a laser cutting machine. And that sort of, let's say, design prototyping was covered very, very well by our colleague Milos earlier this morning in the presentation. So we got a very similar process in which we also used the laser cutting to build this box in this project specifically. And number 6 shows you more or less what the inside of the box looked like, where with the table where you can put the, it's your device, your phone, any tablet, anything you want to disinfect really, you can have it, and it could be disinfected within seconds. So now, after we have a certain design process, we have a prototype. Now it's time to, after gathering all this information and learning from all these mistakes, is to switch to integrating a final build. And for that, my colleague Mohammed AlKaabi will walk you through them, and hopefully you're gonna find all this information that will make sense and add up in a logical way.
Thank you so much, Mohammed, for going through the design. So now, since we finished our brainstorming, did our research, and have some designing, first sketches, 3D models, testings, some simple circuits. So after we've gone through these steps, the next step would be integrating some kind of a final build of these ideas that we had. So these are some pictures from the 3D masks. As you can see, after printing the 3D mask using 3D printers available in the Makerspace Zeina, we got some strings for the mask, some 3M filters, some face shields material, as you can see in the top right picture, and some cushions, for example, and we have printed multiple 3D masks. So this is for the 3D masks. As for the ozone chamber, so you saw in the beginning that we had some kind of an initial sketch where we have a chamber and we have an ozone generator we have disassembled. So in this case, actually, this is one of the new things I would say that it was interesting that we had to make some kind of wooden box. So we don't have a lot of experience with woodworking, but thanks to the people in the makerspace, that had some experience with woodworking and such like techniques and such talents. So we were able to make some box for the chamber, so it will be closed and sealed. As you can see, we have in the inlet we have an input, which is the ozone from the ozone generator, and we have also a sensor to sense the concentration of ozone. So you can see on the right picture the overall assembly where we have a box. So the goal is to be able to put something like a ventilator or put some kind of a PVE that can be then closed and disinfected for a certain amount of time, depending on the size of the box. So I will go through the board, the control board, as we call it. So first we have on the top left the schematic of the overall system. So the control system, where we have ozone sensor, and we have a relay that will control the ozone generator. So mainly the board, which is actually printed, laser cutted using the laser cutting machine and etched to know where's the location of every part. So we have two parts. The one on the right, which is the ozone generator, and its air pump and the power for it. And on the left side, we can see the control board and the screen showing, sampling and the status of the system, where it's sampling and the ozone concentration, and where we are able to control the ozone generator depending on the concentration. So we will try to fix it at a certain concentration for a certain time. So I would like to go for the UVC box. So you saw in the first the design phase by my colleague Mohammed that we used also laser cutting to make the box. So with some simple sketches and laser cutting drawings, we were able to make this box with hinges and so on. And you can see in the left picture we had a table where we can put our object that we want to be disinfected. You can see also the hinges of the doors. And on the right picture, you can see the system, the box from inside, where we covered it with aluminum foil, so it will reflect the light from all places. So the disinfection would be, the light will cover most of the area. And you can see we had two light bulbs, and so we can cover most of the area of the object. And you can see also on the bottom left of the picture a magnetic sensor that will be used, later on for also the control circuit of the system. So you can see we have the indication, we have three lights for when the door is open. As we saw in the research that UVC have some effects on the skin and also on the eyes. So for that, we used this sensor, the magnetic sensor. So if any case, in any case someone opens the door, the disinfection and the UV light will turn off immediately because of the effects of the UV light. Otherwise, we can put a certain time, and it will disinfect the object as soon as we close the door for that period of time, and then it will turn off the light until we open the door. So these are the final builds, say, of our project. And as final thoughts, after doing this project in the Makerspace and using laser cutting machine, 3D printers and so on, we have some final thoughts on our experience. So we realized that having any idea with the right equipment, one can solve almost any problem actually. So just having the idea and the goal, we can solve any problem. And the second thing is that fast prototyping also has been proven an effective approach in solving unprecedented problems like the COVID problem. Also, disinfection of viruses is based on commonly used methods. So UV light and ozone is not a new technology, but this is something that we discovered through research that it can be used to solve other problems. And two things also, that the ability mass produce a prototype is very critical in the design process. So in the beginning, we thought that this thing can help if we mass produce it. So this thought is very important throughout the design process, and also that many problems can be faced during the prototyping. For example, getting like the ozone sensor and making sure it's working. Some problems in 3D printing, or some problems in laser cutting or woodworking and so on. So these problems are very interesting to try to solve. And finally, the most important thing is that joining forces and teamwork is really the essential factor in any project. And for that, we would like to again thank everyone that was part of this project and gave us the chance to present this on their behalf. Thank you.